Hello minions, welcome back to Nick Does Maths. Do I have a doozy for you today? I have gone scouring the depths of the Lungang Reddit subreddit and I found this question. It was right there, right? Someone posted this. There's been a few comments about doing this sort of thing. This one is very algebra heavy, but it's quite cool. But you're going to put the whole question up on the screen, sort of now-ish, somewhere here. I don't know. Pause, go have a look, write it down, go check it out on Reddit. I don't have space here to write every single element, but here's the crux of it. We've got the plane ax plus by plus cz is d. We've got a line in 3D, x minus x naught, etc., etc. Now we're going to reflect this line in that plane. And our claim is we've got this new line going to the point x naught tilde, y naught tilde, z naught tilde, and with these components, a naught tilde, b naught tilde, c naught tilde, where if you look at the full question, we've got expressions for x naught tilde, y naught, and z naught, and for a naught, b naught, c naught tilde. I've only put x naught and a naught. We're going to see how to get these. The other results follow exactly the same way. You'll just pick out a different line from a vector. All right, so I'm going to show you how to do these. You can pick out the other ones yourselves. So I think the first thing to realize is, to have a think about, is how we're going to deal with the geometry of reflecting something in a line, in a plane, in whatever it is. So let's start with... I think actually, so once we get our idea on the main crux of the maths here and the geometry, it's actually not too bad. And I think I am going to start with, let's have a look at this. Okay, so first thing to realize, of course, is that this is R dotted with A, B, C is equal to D, and A, B, C is our normal vector. Our normal vector right there. That is our normal vector to the plane. And same point for our line here. This is a line going through x naught, y naught, z naught, and the direction vector is a naught, b naught, c naught. Okay, so we've got our normal vector to this plane is a, b, c, and we've got the direction vector of this line, a naught, b naught, c naught. I much prefer the vector form rather than these Cartesian horriblies, but that's just me. So to find the equation of this line, what we really want is we want to find out a point that will be on the line and a direction vector. And we're going to do both. So I think we're going to start with the point. Let's see what happens. So a natural candidate for x naught, y naught, z naught tilde is the point on the line. It's just the reflection of this point in the plane. So what does that mean for me? Well, let's say I've got a plane, right? We're looking at it face on, and the plane has a normal vector. And this is my point, right? This is my point. Now, how am I going to get my reflection? Well, what I want to do is I want to take the point, go perpendicularly, and end up there, okay? So what we want is a couple of things. We want the distance here between a point and a plane. Now, the shortest distance this is the point x, y, z, and this is the normal vector a, b, c. Then standard, I think it might even be in most formula booklets, the shortest distance from a point to a plane is you plug this point in, ax plus by plus cz minus d, over square root of a squared plus b squared plus c squared. All right, and in fact, let's keep the same notation as this question, x naught, y naught, c naught. All right, so this is my actual, there we go. Now we're using the same notation. All right, so I want to reflect this. So what I would quite like is to find what this vector is. What is that vector? Well, it's going in the direction of n, right? D is probably poor notation. What should we use for this? L, length. All right, let's call that L, whatever that term is. So this green vector is what? Well, the green vector is some multiple of n, and it has to be this length. So it's a multiple of n that is this length. So how do we do that? Well, this vector then, the easiest way to do that is divide n by its modulus to make it length 1, and then multiply it by that length. All right? That's the easiest way to do it. And we're going to do this time and time again. In fact, this sort of idea is very much where we get this from in the first place. But there we go. So this is what we want to do. This vector, to get me from the point to the plane perpendicularly or orthogonal, if we're doing this properly, is some multiple of the normal vector. We rescale it to make it length 1 and then make it the length we want. Well, the idea is, well, we just need to, that will be the same vector as there. So this point here is where? Well, it is the point x0, y0, z0. All right, this is my new x0 tilde, y0 tilde, z0 tilde, minus 2 times this green vector. So once minus the vector wants to get there, then minus the vector again to get there. So normal vector times mod n times the length. All right. So let's put all of this together. In fact, let's do this as position vectors. All right, let's do all of this as position vectors. All right. So we are just reflecting our point. How? We find the vector that gets me from the point to the plane perpendicularly, and we go again. So minus twice that. So what's this equal to? Z0 minus 2 times. Now we said L was all of this. Over, well, square root of a squared plus b squared plus c squared is just mod n. So we're going to have it that times mod n, which is just a squared plus b squared plus c squared times the normal vector a, b, c. And as you'll see, we are pretty much there directly. All right. x0 tilde, y0 tilde, z0 tilde. We're already there. So if I just want my formula for x0 tilde, we're just going to look at this first line. x0 tilde is x0 minus, we're going to take that term there, 2a times all of this rubbish over a squared plus b squared plus c squared. Okay? And if you go look at the actual full question breakdown, either at the start of the video, pause it, or go check it out on Reddit, you will see that we have similar results for this, just with, if we want it for y0, if you want it for y0 tilde, you get a y0 and you'll get a b. If you want it for z0 tilde, you get a z0 and you get a c. Nice and easy. All right. I just really like thinking about the geometry of what's going on here. Okay, fine. This one here, check. This is going to be a little bit harder. Although the expression looks nice, we have to do a little bit more thinking. So what about my new vector, the vector for my new line? So we found the point that my reflected line is going to go through. All right. If the point x0, y0, z0 is on L, x0 tilde, y0 tilde, z0 tilde will be on L prime or L tilde, my reflected line. So let's have a think about the old man sounds. Let's have a little think about the the direction vector of this new line. So first thing we might want to do is, how do you reflect a vector in a plane? All right, we just looked at it with a point. Right. So let's say we've got a vector coming in. Okay, vector v. Now, let's say we have a normal vector n. In fact, let's exaggerate this a little bit. Let's exaggerate this a little bit. We will get our reflected vector w. So the key thing here really is, how can I express w in terms of v? Here's the trick. Here is the trick. let's say I put v there instead, right? Same idea. Same idea. I could put v wherever I want. Vector doesn't have to be in any particular place, right? Same length, same direction. What we are going to look at, and let's stick with some blue for a bit here, is in fact, how can I get w from v? Well, if I just add on this blue vector twice, you can see a similarity to what we just did. All right. Whatever this thing is, let's call it v, I don't know, star. I call it v star. Then I can say that w is v plus 2v star. Well, what is that v star? What is that v star? That's very interesting. Well, v star is some multiple of n, is going in the direction of n. So v star itself is some multiple of n. Now, what is that multiple? Well, what we want is we want it to be this length here. All right, let's go for L again. We want it to be that length there. Okay. So where do we go from here? Well, we are down to a little bit of geometry. Let me just check my crib sheet and see how we get on. Now, if I were to take that angle there, I could say that that length is the length of v cos theta. All right. Now, here's the trick. Here's where we go. I can get that. All right, let's actually call this phi, something like this, cos phi. Let's call it phi. Because if we have a look at that, right, if I look at that angle, the angle between my vector and the normal, we can say that cos phi is minus cos theta. Now, this is going to be really important for me because I can find cos theta, because I know that n dotted with v is mod n mod v cos theta. So, what do I end up with? Let's put all of this together. This length here is minus mod v cos theta. All right, that's not a vector. So this length here is, what did we say cos theta was? If we look at this, v cos theta is that this is minus n dot v over mod n. We're getting there, I promise. Right, so what do I want k to be here? Well, I want this vector to go in the direction of n, fine, some multiple of n, and I want it to be length L. Well, what's the best way for me to do that? Well, same as before, we will make that L over mod n, lots of n. Okay, so we're going to take our normal vector n, make it length 1, and scale it back up. And now we're about set. We're about set. So if we go back to here, plug it all in, we get that my reflected vector, and I'll pop that down here, my new reflected vector is v plus Oh, no, we're going to pick up a minus. All right. Plus 2 times, and I'll sort that out in a section, actually, V star. V star is L over mod N, which gives me N dot V over mod N squared times N. That is how we are going to reflect it. All right, let's see where all this comes from. L over mod N, if you look at this, divide this by mod N, we get a mod N squared. Okay, the 2, because I need to go twice up. So this is my vector reflected in the plane. This is my vector reflected in the plane. And now we are set. Now we are set. Right, I'm going to need a little bit of space here, but this is my result down here. So this is my reflected vector. If you reflect V in a plane with normal vector n, this is how you get your reflected vector. Right. Let's bring all of that into here. So we want to reflect A0, B0, C0 in a plane with normal vector A, B, C. So all we need to do is use this, is that V is A0, B0, C0, N is A, B, C. So my reflected vector, and I'm just going to call it W for now. We'll play around with that in a second. So it's my original vector, A0, B0, C0, minus 2 times. Now, N dot V, A0 plus B, B0 plus C, C0, over A squared plus B squared plus C squared times A, B, C. I'm going to shift that back over here because you might be getting a bit of glare all the way over there. Now let's just have a little look at what's happened here. We've got a lot of the terms that we think we might want. I see you got these BB zeros, CC zeros there over here. We've got some B squares and C squares. So what we're going to do, I never said, so when I want the direction vector of a line, I don't need it to be the same length. I just need it to go in the same direction. All right. And what I can see from here, right, is the components of their one that they want doesn't have this divided by A squared plus B squared plus C squared. So what I'm going to do is I'm going to times everything. I'm going to say basically that my A0 twiddle, B0 twiddle, C0 twiddle is going to be everything times everything by A squared plus B squared plus C squared. All right. That's A0, B0, C0 times A squared plus B squared plus C squared minus 2 times A0 plus B, B0 plus C, C0. All of that times the vector A, B, C. You could be forgiven for thinking that, whoa, we're nowhere there, but in fact, we do. We have 1. If we take this one, we're only going to look at A0 tilde. Like I said, you can get equivalent ones for B0 and C0 by looking at the other line. So I'm just going to look at the first line here. A0 tilde is A0 times A squared plus B squared plus C squared minus 2A times A0 plus B, B0 plus C, C0. That's just that first line. So I picked up the A. If you want it for B0, you'll pick up the B, you'll pick up the C, and so on and so forth. But what we can do, and this is where it's a little bit funky, but you'll notice I've got an A0 A squared there. I've got minus 2 A squared A0 from there. So what I end up with is A0 B squared plus C squared. A0 A squared minus 2 A squared A0 is minus A squared A0, and that's going to go in there to give us this term here. And then minus 2A B, B0 plus C, C0, and I'm close to the board there, so I'm not going to be able to see everything. And that is our one last step. Bring that into there. We are all good. Nice. Like I say, a lot of algebra, but what's really interesting about this question is getting your head around the geometry of what's going on in here, in order to reflect this vector V into this vector W. And we got this really nice idea in maths of if I want to make something a certain length, you rescale it to 1, divide it by its own modulus, and then make it the size you want it. And that's quite a nice little trick as well to have in your back pocket. Yeah, I thought it was a really, really funky question. I mean, it's very, very pure, right? Very pure. Really, you are deriving here the general results for reflecting a line in a plane, right? This is absolutely generic, a generic line, a generic plane, a generic line. We end up with a generic statement here. And we're up and running. There's a few manipulations we could have not done. We could have just kept this as my reflected direction vector. We could have just kept this, but it's a little bit nicer without the fractions. So we just scale it up a little bit. So in our case here, our reflected vector W will actually be bigger. It'll be longer than V. It'll be slightly longer because we've scaled it up. Lovely. I think that's everything. I think that's there. Again, as a nice, neat exercise for yourselves, go make sure that you can get the same results for B0 tilde and C0 tilde. If you found this interesting, don't forget to drop us a like, a subscribe, hit the bell so you don't miss any videos as they come up. There should be a link in the description for the Easter Revision courses that we are running that are coming up. Do check them out. 2 solid days of doing further maths with me. We're going through all of the core pure content for the further maths exams and some mechanics and some statistics, which will be relevant to a variety of different boards. So check out the link and hopefully I will see you there. I'm Nick. We did some maths. I will see you soon.